and let's review these examples. So we started projection at an angle, right? Different to horizontal projection in that there's sort of two components to it. We have to divide these problems at that maximum height where our velocity changes to 0 and then flips to becoming negative. If we do the mathematics, like if you know quadratic equations, for those of you who are familiar with quadratic equations, that nice parabolic curve, an x squared value sort of thing. When you solve them for a position on an x-axis, you often get two solutions, right? Now that makes sense logically in physics as well. The launch height and the landing point, you'd get two solutions for any value of y. Generally, when you solve quadratics, you solve them when y equals 0. So you're at your origin, which in a physics problem would be the ground. So you get two solutions, launch height and landing height, okay? But that does complicate the mathematics, and we want to avoid that. So we break this problem into its symmetrical parts, and you can actually do that with quadratic equations too. They're symmetrical. Once you know that turning point, that maximum height, which we find by setting velocity to 0, okay, at that point our y velocity is 0, we can then navigate either side of that, no problem. All right, so that's what we're going to continue doing here. Now we started this example 1. We found our x and y components of our initial velocity, u for initial velocity, x and y for horizontal and vertical respectively. And we did that using some simple trigonometry. We turned that into a triangle, tip to tail with our vectors, make our resultant vector. And we're now looking at the maximum height, and I believe we ended up calculating that. And remember, that maximum height, that is that point where that velocity equals 0. So we say find sy, find the vertical displacement, when our y velocity equals 0. And then we just sub those values in, everything that we know, into the relevant formulas, and we can solve. As we're doing this, you may want to make note of exactly which formula this is useful for. Okay, so you can say, useful for case 2 of projection at an angle. You can put a little annotation on here to remind you when you're flipping through your notes, which sort of formulas should you be looking for. But it does depend on what you're given in the question and what you're asked. So you'll have noticed a change in the format of how I've been teaching this. I haven't gone, here's the theory, here's the formulas you'll use, okay, let's do an example. It's just straight into the examples, because all of those formulas in your formula data book could be used at any time. So we need to become familiar with each of them, and we'll do that just through practice. But as we're doing that, you might find it useful to quickly annotate, hey, this has come up in this situation, this has come up in this situation, because there are some common situations where certain formulas will be more common, okay? I'll leave that up to you to decide, though, if that's something you think would be useful for your notes, depending on your process with your note-taking. But for now, we'll just continue on with this example. So we found that maximum height, and the next part of this problem asks us to find the time of flight, okay? So we're now looking for a t. Now remember, when we're talking about time, we're almost always talking about delta time, a change in time. We want to know a difference from when this thing started flying to when it stopped flying, basically. That is a change in time, okay? We often use just t, all right? So if we say c, we're going to find t. We often use t to mean delta t, because there's not really any other way to use t. There's no absolute time, it's all relative, right? We'll get into that in Unit 4. Now, I want us to list out everything we know about the time problem that we're now imagining. So we want the time of flight. So we're talking about when we start, we just leave the ground. When we land, we just hit the ground. What do we know about that whole situation? We know an initial velocity, yeah, in the x and y. So known. Let's identify our known variables here. We know our initial velocity ux, and we know our initial velocity uy. Don't give me any resultant vectors here. Give me just the components, just the x and y components. Do we know anything about the final velocity? Let's start with the final velocity in the horizontal direction. Do we know the final velocity in the horizontal direction for this example 1 where this ball is flying a bullet is flying around like this. Remember, it's going to go like this, blah, blah, blah. This is projection at an angle. There are certain rules about these cases we got introduced to on the previous page. What do we know about the final velocity in the x direction specifically? Come on, guys. We know this for every single projection problem. Are we accelerating horizontally? What's accelerating us? Are we a rocket flying, accelerating? Is there something propelling us horizontally? Is there air resistance in any of these problems? No. So is our velocity in the horizontal direction only, independent of what's happening vertically, purely horizontally, is our velocity changing? So what's our final velocity? We know what it is. It's ux. Vx is known. What about our final velocity in the y direction? Now, this is where projection at an angle comes into this, and this is where we have to understand the differences between the different scenarios we're describing here. This is case 1. What do we know about the final velocity in case 1? In the y direction. Guys, stay switched on for me. This is really important. Sam? What's the annotation for final velocity in the y direction? What symbol are we looking for here? V? V what? Are we talking about horizontal x or vertical y? We just did horizontal, remember? So I need you guys to switch on and ask questions if I'm losing you, yeah? I just told you that ux and vx are the same, okay? So now we're looking at uy, and hopefully we know something about vy. We might not. It's perfectly plausible that we don't know what vy is. But I want you to think about the context of the problem that we're solving here. What is our... Do we know what vy is? What is it? Negative uy. It's right there, highlighted in pink. Yeah? Let's switch on, guys. Wake up. So uy, we're going to have an initial vertical component of our velocity. Now in case 1, when we land, we are perfectly symmetrical. It's just that our velocity is now directed downwards, okay? When you throw a ball up and it reaches its peak and then it goes down, the acceleration is constant the whole time. So for it to decelerate to 0, it will then accelerate by that same amount negatively. So the only change is its direction in its velocity. So uy is now negative vy. So vy is known. Now we're trying to find time. Let's have a look now at our formulas and start trying to identify. We know all of them, okay? We want to find t. Let's start looking at those formulas in our formula and data book that we all have sitting in front of us and try and identify which formula might be quite useful here. Let me bring mine up on my computer. Just give me a second. So someone said the second one, do you mean sy equals half gt squared plus uyt? Is that what you meant? Yeah, okay. So one of the formulas we're considering right now is this one here, sy equals half gt squared plus uy. So it relies on, it has time in there, which is great. We can solve for time. We know g, that's acceleration due to gravity. So this is all vertical components. We identified uy, that was known. Sy, do we know sy? Do we know how much this ball has displaced vertically? Yeah. What did we find right here? What's this? What is this? Sy max. Is that what they're talking about here when we're trying to find the time of flight? Are they talking about the situation where our height is maximum? Does that describe the time of flight? No. So this is the key conceptual understanding, Nicola and Kobe. The key conceptual understanding here is that we're no longer looking at that maximum height, we're looking at the whole problem. Two ways of solving this. One, you find the time of flight to that maximum height. And guess what your total time of flight is? Double that, because it's a symmetrical problem. However long it takes to get to that max height is the exact same time it takes to get back down. Yeah? Doesn't matter how fast it's going horizontally. Throw a ball up, how long it takes to land is just double the time it takes to get to its maximum height. Acceleration is constant. That's one of the things we know. Okay? Alternatively, you can set displacement to be 0. Yeah, the ball has not displaced vertically. Guess what that looks like? And I'll jot it down over here just quickly because we're not actually going to do it this way. It looks like this. 0 equals half g, so 4.9, some number, right? 4.9, we can write 4.9. T squared plus uy, which is some number. What was it? Did we find it earlier? Uy, I can't remember. It was like, we put it as, no, we put vy as 0 there. Here it was, oh, sorry, you might be right. 129, yeah, that's right. Plus 129t. What does that look like to you guys? Quadratic. A quadratic. That's a quadratic equation with the two solutions for y equals 0, okay? And you can solve that, and I'm not against you using that approach. I would suggest, though, that it's harder than it needs to be. What's the easier way of doing it? Solving what? Vy equals gt plus uy. Why can't we just use that? No? We know what Vy is, our final velocity. We know what Uy is, our initial velocity in the y direction. We know what the acceleration is. We can very easily calculate how long it takes to hit the ground. Yes? Let's do it that way. Like I said, you can do it with a quadratic. It's just not as easy by a long shot. So let's take this formula, let's go on to the next page. Again, I'm going to go through the second and third examples as well, but we're going to go on to the next page and use this formula now to solve this. So we know Vy, we can skip back 2 pages to find that. Uy is just the negative of that, or vice versa. We know G, obviously, so it should be pretty straightforward. Let's do that now. All right, so we're on example 3 here. Let me just set up my page again. You guys have had to go over multiple pages as well. I do encourage you to relabel which example's which at each stage. Okay, Vy equals gt plus uy. Now, to be fair, this only works with constant acceleration, but that's the case we're dealing with. Gravity is our acceleration, so these are all known. So Vy was, well, let's rearrange for t first because it's very straightforward. Vy minus uy over t equals g. Over g equals t, sorry. Finding g would not be useful. Equals t. Does anyone want to see that rearrangement done fully? Jot it over here. Can we see what we've done? Subtract both sides by uy. Divide by g equals t. Okay, now positives and negatives are important here, so when we substitute in our values, we really need to consider that. Our final velocity, oops, too far. Our final velocity in the y direction is the negative of our initial velocity, right? Did I even click that page? Take me back here, please. So here's our initial velocity in the y direction, 129 meters per second, positive because it's moving upwards. Let's take that and state that as uy. We're going to have minus 129 meters per second. That's our uy. Right? What's our vy? It's the negative of that. That was positive. We're just subtracting here. So subtracting positive 129. This vy, we need to sub in negative 129. Okay? Everyone okay with the negatives there and the subtraction? And we're dividing by what? What's our g value? Say it again. Thank you. Yes, negative 9.8. If I do this with a positive, I get a negative time, which is completely illogical. And there's a reason for that, because it's wrong. Okay? We need a positive time here. T will equal, what's that? Negative 258 divided by negative 9.8. Somebody do that in their head real quick. You did indeed. 26.3, let's go 3.3. Woo, that's a fun 3. Had a tumor. It's not a tumor. Okay. How are you feeling about the time of flight there? Yep. Pretty wild. Any questions? Anyone want to check a step? Anyone need me to re-explain a step? No? All right, let's move on to the next one then. Next part of this problem, and the final part, I believe, is displacement in the x direction. Sx, guess how easy it is? D, find Sx. We know that the time when our flight stops is that. So we know time, we know our initial velocity, right? Sx equals ux times t. Distance equals velocity over, or times by time, right? How fast is it going? How long is it going that way? What was its initial velocity in the x direction? 120 something as well? 153 maybe, yeah. Hang on. Check it here. 153, yep. Positive to the right, of course. 153 times by 26.3, oops. 26.33. I think I still have my calculator up, so I just multiply my answer for the time by 153. The bullet travels 4,027.96 kilometers. Let's think a little bit about significant figures. The original problem gave us 2 digits. Technically both of those are only known to one significant figure, which I'm okay with. 4 kilometers. Oh, sorry, that should be meters, not kilometers. Is it not letting me undo for some reason? Okay. That's in meters, which is approximately 4 kilometers. All right. What a problem, hey? Now, I think it's fair to say that that's the easy version, case 1. Because of that symmetry, things are directly the same. But the reality is we could have done all of this math exactly the same, okay? This here, for example, uy, vy, yeah? They wouldn't be equal, but you can still calculate final velocity. You can easily still find final velocity. So a lot of this would still be the exact same process for the other example. We're not going to do example 2 today. I'll leave example 1 there, that's done, and I'll give you an exercise on that to practice yourselves for the rest of this lesson. I think that will be a better use of our time today. And then we can look at the other examples later. On Thursday, we are doing a practical where we are projecting at an angle, okay? Yes, you finally get to do the catapult pracs. So, they're more like a cannonball prac anyway. I'll put up your exercise, I'll leave you to it, and we'll call it there for today. Yep. All right, here we go. Let's do... What I would suggest is you make sure that you have space to do example 2 and example 3, okay? They won't be as long. We'll just do a couple of parts on them. We won't do time of flight, horizontal distance. We won't do everything on them, okay? So they shouldn't be as long, but make sure you have enough space in your columns for those 2 examples. And then start your exercise.